Let's jump right into it and look at what the residual emissions will be that need to be removed in addition to the mitigations of greenhouse gases we have been talking about throughout the course. So starting here in 2020, if we want to hit below 2 degrees C target, we should already be decreasing or mitigating greenhouse gases. So here is showing in gigaton CO2 equivalent per year, and we have repeated several times that business as usual is going to go this way and maybe start coming down after 2060 or so. And unfortunately, as we said, despite all the negotiations, we are almost on this trajectory as of 2020. COVID lockdown had some effects, but already we are back to normal. Okay, so here is the mitigated GHG emissions, and that is still above the net zero GHG emissions needed by down here at 2085 or 2090. And that's because we have what are called residual emissions. So two trajectories for future greenhouse gas emissions showing all greenhouse gases as their equivalent in CO2. Red curve would give us a 66% chance of reaching less than 2 degrees C by 2100. Brown field represents the current efforts. So essentially the message again is that despite the commitments made under the Paris Agreement, the nationally determined contributions and so on, we are not on target to staying below 2 degrees C. So forget 1.5. We're going to blow past 1.5 probably in a couple of decades if things keep going the way they are, right? And so this is the definition of residual emissions here. They are the emissions remaining after all technically and economically feasible opportunities to reduce emissions in all covered scopes and sectors have been implemented. So technically feasible, economically feasible. So we'll look at we'll look at things that are technically feasible, like direct air capture. 0.04% is the concentration of CO2 in the atmosphere. This is a great challenge for us in terms of taking it out, but it's also a great challenge for technology people to draw down such a small amount that is there in the atmosphere. So it's a trace amount, but it obviously has huge feedbacks and important for greenhouse warming. So it's a question of things that may be technically feasible but not economically feasible. So you end up with some emissions like from transportation and I don't know, you can look up the examples which are right now going to give us residual emissions. Okay, so here it is talking about again the CO2 and other greenhouse gas drawdown needed from already right now. We are a little bit late. This is called the wedge. So the green wedge here represents the negative emissions or removal of CO2 from the atmosphere required to offset residual emissions from other greenhouse gases. So you have CO2 removal, but you will have other greenhouse gases here removing, and there is our 2 degrees C target running through there. So here the definition is this is the gross negative CO2 emission, which targets all emissions in all sectors to bring them to uniformly zero, whereas net zero allows some residual emissions in sectors where abatement is either too expensive or technologically not possible, on the assumption that they will be offset by deeper cuts elsewhere. Okay, so we have to still go below here in terms of greenhouse gas emissions, but residual emissions have to be compensated for by deeper cuts elsewhere. Gets a bit technical, but this is something people who are going to work on technologies and returns on investments, co-benefits and so on have to worry about, right? We need to be aware of as students of this course. 5 methods that are listed here with approximate values of how much annual negative emissions they may provide. So we'll look at the potential. Regrowing forests, 1 to 5 billion tons per year. We will see that actually this is maybe a little bit optimistic, especially when you look at wildfires all over the world. The ones that go out of control over California, Australia, and other parts like Canada and so on. So there is always that question of how do you protect forests from perturbations, deforestation and degradation and so on. Putting CO2 back into the soils we have talked about, 450 billion ton total, but this is slow with only 2 to 5 billion tons per year. Using biomass to remove CO2, where you grow things specifically for energy sources where CO2 is removed along the way, so either while making fuel and energy, or to restore soil carbon. Again, it's 2 to 5 billion tons per year. So this is enhancing carbon sinks, as we talked about, by reducing in agriculture, landfill, food processing, etc., that we talked about. Whereas this is producing biomass specifically for making fuel and energy, so that you are going to make it a kind of a circular economy where CO2 is drawn down. Enhancing natural reactions of minerals with air. So we will see what that means. Basically, it's like scrubbing methods where air is flowing through and you extract carbon by mineralizing it. So that has a potential of 2 to 4 billion tons per year. Directly removing CO2 via chemistry and machinery, that is direct air capture, limited only by the availability of renewable energy to power the devices, but probably 2 to 5 billion tons per year. So this is they are related. So here we are talking about enhanced weathering, for example, whereas here we are allowing air to flow through. It's almost like an artificial tree, which is being designed by Gary Lackner and others. Okay, biomass and direct removal methods generate CO2 that must be stored permanently out of the atmosphere. So nothing is free. Plants do respire, even though they are building carbon biomass. They are not necessarily carbon neutral by themselves. These approaches also have limitations. Making carbon-based products from CO2 instead of oil. A lot of the plastics, rugs, carpets, various materials for vehicles are all made from petroleum because it's easily available. Processes are in place and obviously much more dense than CO2, but there is a potential of using CO2 to make these products with 1 to 5 billion tons per year. Putting CO2 underground as liquid, theoretically it has unlimited capacity, but it can be expensive. So one has to always worry about making sure that any method you use is actually net zero carbon or net negative. Plus, you have to worry about whether it's economically feasible, even if it becomes technologically feasible. These are all the challenges we will look at more specifically with each approach.